Construction catastrophes come in all shapes and sizes. A railroad bridge brought to its knees.
The valley just looked like you would expect after a battle.
A massive waterway washes out one problem, but ushers in another.
5 to 10,000 of them just erupting out of the water.
And a fairy tale town living through a nightmare.
It's an earthquake in slow motion.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, these are the engineering catastrophes that only an expert can hope to fix. When it comes to revolutionary design, sometimes we can learn from the past, other times we can improve on it. But rebuilding on an old foundation can be a huge mistake. For this construction calamity, we head to Pennsylvania, USA, and a famous bridge that fell from grace.
This is a massive fail. It's utterly incredible that no one got hurt.
If a train was going over it, it doesn't bear thinking about.
What was once considered the eighth wonder of the world is now a relic of engineering oversight. The small town of Kinzua, like many other places in Pennsylvania, was central to America's steel production. In the 1880s, demand spiked and trainloads of coal were needed to feed the factories.
Railroad engineers faced a giant obstacle, the steep, deep Kinzua Gorge off the foothills of the Appalachian Mountains. The trains had to get through, so they set to work on one of the most ambitious construction projects of the day, the Kinzua Bridge.
Completed in 1882, at over 300 feet tall and 2,000 feet long, Kinzua Bridge was the tallest railroad bridge in the world.
At the time, this was pretty much the eighth wonder of the world. It was such an unbelievable achievement. Even with today's technology, this would be a challenge, let alone back in the 1800s. So to actually achieve a viaduct over that size gap was incredible.
Jerry Clark from the Bridge Foundation knows what made this build so epic.
Other railroads went around the Kinzua Valley. The bridge went across it and used every bit of the engineering technology available during that time.
To achieve this shorter direct route, the bridge had to be high, long, and capable of supporting heavy coal trains. Engineers ruled out the conventional bridge-making materials, stone and cast iron, instead choosing wrought iron.
Building a bridge of this size out of stone or brick would have taken forever, and using cast iron would have been too brittle, so they looked to wrought iron as a suitable material.
Wrought iron had another advantage too. It's malleable. So they used sheets of iron to create an innovative support structure known as phoenix columns.
These phoenix columns were made out of wrought iron that was folded around and held together with rivets, and this made them stronger and lighter.
The revolutionary design was also quicker and cheaper to build. However, within a decade, locomotives doubled in weight. This meant more strain on the bridge and more vibrations.
Vibrations are not a bridge's friend. You expect them up to a point, but here we had a tall, long bridge with trains going over. The trains were getting heavier and heavier. They had to be careful not to push it too far. The material could withstand it to a point, but whatever they did not want that material to crack.
To minimize vibrations, trains were forced to cross at just 5 miles an hour. Not the most practical solution in a fast-moving world. Fortunately, an alternative was now readily available: steel.
At the time, steel was the strongest, lightest and most flexible bridge-making material around. So it sounds crazy, but they actually ripped the old Kinzua Bridge down and rebuilt it in steel.
No bridge meant no coal, so a quick construction was essential. And in just a matter of months, 120 men erected the new bridge.
90 days is all it took to completely rebuild the longest railroad bridge in existence.
The new steel bridge used the original trestle design, with large A-frames supporting the pier on top. It could now carry as much coal as the steel mills needed. But in an effort to save time, a decision was made that would turn out to be disastrous. Rather than installing new steel anchor bolts to hold the bridge in place, the legs were secured to existing bolts. They were too short, so engineers used extending nuts called collars to bridge the gap.
So replacing these anchor bolts would have taken forever. You would have needed to dig out, blast away. It would have been a real hassle. So instead, they just put these collars over the top of it.
At the time, the collars seemed a reasonable solution, but they hadn't completely factored in Mother Nature.
This quick fix did the trick, and the bridge carried freight and passenger trains for over a century without incident. In 2002, a maintenance team discovered corrosion on the bridge's legs. They closed the bridge to trains and pedestrians and began repair works. But in the summer of 2003, disaster loomed. An epic tornado spiraled towards the Kinzua Gorge. In 2003, engineers were repairing corrosion on the Kinzua Bridge in Pennsylvania. But in July, disaster struck when a powerful storm raged up the valley. Structural engineer Brian Emberg was on the restoration team.
In July of 2003, I got a phone call, middle of the afternoon, that a tornado had hit the bridge. I jumped in my vehicle right away, made the trip, and got here right about dusk, and it was clearly a tornado scene, trees everywhere, clouds and mist. I met with the crew and made my way down here to the edge of the ravine, and turned the corner, and the valley just looked filled with smoke like you would expect after a battle. You could barely start to make the structure in the fading light, and you could see pieces of steel emerging from the fog, and then what was remains of the structure still standing. It was clear it was a catastrophic failure.
The 100-mile-an-hour tornado had sent a huge section of the bridge crashing to the valley floor.
This must have been so frustrating. They were on to this problem. They saw it. They were acting on it. So if it struck a few months later, they would have been fine. This is such bad luck.
Although devastating to the repair team that spotted the corrosion, closing the bridge had potentially saved hundreds of lives.
To have such a freak of nature storm come in and take it down was really devastating to my crew, my team, and me personally, that we weren't able to get to it and save it in time. Had the tornado arrived a year later, we'd have finished with the repairs and hopefully sustained the structure so it would have survived the storm.
The day that it fell down in there, you kind of felt like you lost a family member.
Brian and his engineering team suspected the original iron anchor bolts and new steel collars were to blame. And their suspicions were confirmed in the wreckage.
So the next morning, I went down to the valley and found these anchor bolts and couplings littering the floor everywhere of the valley, where they had ruptured and failed at almost every single pier.
Although steel was clearly the stronger and more flexible material, the bridge's iron anchor bolts didn't fail until the tornado of 2003.
The problem was that the original designer didn't think there was going to be uplift. An uplift comes from wind blowing on the towers. When wind blows on the tower, it wants to try and overturn it, and so on this leg, there would be uplift. The original designer, he used these because he didn't think there would be uplift, when in fact there would be with a 100-mile-an-hour wind. And it turned out to be inferior, especially after years of wear and tear, and it cracked.
A combination of extreme weather and the decision not to replace the anchor bolts over a century ago was the undoing of this epic piece of engineering.
This was a hugely ambitious project, and at the time it really pushed the boundaries of engineering knowledge, and it looks like a tiny miscalculation, and the use of these collars unfortunately led to the demise of this bridge.
Today, around 600 feet of the structure still stands. Rather than tear it down, it was kept as a monument to mankind's ingenuity in engineering.
Everything here could have been scrap metal, but there were people that had the foresight to say, this is worth saving. Actually, there are more people that come to the bridge after it was down than when it was up.
To prevent any further collapse, Brian and his team have devised a solution. It's no surprise that it includes steel anchor bolts, an idea that the original engineers overlooked.
When it comes to the foundations, you should never cut corners. It may have taken over 100 years, but that lesson was learned in spectacular style.
Next, we head to northern France and a cathedral that's experienced a catalog of catastrophes.
This one is a blockbuster of a building blunder.
It seems the engineers' zeal to reach the skies clouded their better judgment.
This cathedral has been the victim of a combination of tragedy and folly.
And when modern-day engineers tried to make a fix, it almost ended in disaster.
It's a miracle it's still standing.
Beauvais, a small city in northern France. But there's nothing small about its 800-year-old centerpiece, the gravity-defying Cathedral of Saint-Pierre.
So we've got Sagrada Familia, yep, Notre Dame, yep, St. Paul's, but St. Pierre's of Beauvais?
Although little known outside of France, the ambition of this cathedral once rivaled any other on Earth. Dr. Tom Nixon is an expert in religious architecture.
Beauvais Cathedral was begun in the 1220s by an extremely ambitious archbishop, Bishop Mars of Nanteuil, and his vision for this cathedral was really something that would trump all the other major churches in France and the region.
Most cathedrals are designed in the shape of a cross, with three main sections: the choir for the clergy, the transept, which forms the arms, and the nave for the congregation. The nave is often long and grand, but here there was an obstacle.
Now, Beauvais could never be particularly long because the site was constricted by the presence of the bishop's palace at the West End. So it could respond to the ambitions of its patrons by being, first of all, very wide, but it could also be very, very tall. And this church, as built, was taller than any Gothic building ever built.
And size was very important.
With cathedrals, just like stadiums and concert halls, the aim is to have as much space as possible under one roof. But of course, the taller and wider you go, the bigger the engineering challenge.
And the greater the chance of making catastrophic mistakes. On close inspection, the grandeur of Saint-Pierre is overshadowed by centuries of repairs that literally hold the building together. And it's all because the original engineers were more focused on height than stability. In fact, their drive for height was so relentless that they had to hold up the tall, unstable walls from the outside.
So it's really remarkable to be able to come up here to the upper parts of the cathedral. Up here we can really get a sense of the way that this forest of flying buttresses supports the upper levels of the choir. And what's really extraordinary, I think, is many of these piers are still super slender.
Flying buttresses act as an exterior skeleton to support the cathedral, but are built to look ornate and elegant, not like mere scaffolding. Engineers hoped these buttresses would be strong enough to prevent collapse.
They're working very hard to ensure that the windows are not obstructed at all, so that we have this wonderful kind of sense of vertical thrust from the cathedral, even though, of course, the reality is the very opposite. What we have is gravity trying to pull this building down.
Back in 1284, Saint-Pierre's ongoing battle with gravity came to a head when a fierce storm hit the town of Beauvais. The devastating winds twisted the flying buttresses, forcing them to breaking point. Suddenly, the high vaulted ceiling came crashing down. Beauvais Cathedral in northern France had ambitions to become the tallest in the world. But in 1284, a storm brought its roof crashing to the ground. The city didn't let that stop progress. The damage was repaired and construction continued. In the 1500s, the cathedral reached dizzying new heights, with the lantern tower soaring over the choir. Jean-Lucien Guénon, one of France's chief architects, explains.
At the time, this was the highest vault in all Christianity at 160 feet high. The lantern tower is built in the Beauvais style, and at nearly 500 feet high, the tallest in the Christian world.
The lofty tower was the pride of France, but it had hardly been completed before disaster struck again.
This spire was finished in 1570, but cracks appeared straight away, and the whole thing collapsed in 1573 after the Ascension Mass. Fortunately, there were no victims.
Two massive fails before construction was complete wasn't just bad luck. All of the cathedral's problems stem from one major engineering mistake: building too high without enough support from below.
In the race to tower over the Amiens Cathedral and Notre Dame, they pushed higher and higher before they had completed the lower floors, which now sounds crazy.
Defying centuries of cathedral construction logic, Saint-Pierre's was built with only the start of a key structural element: a nave.
So here we can see the junction of the 10th century cathedral, which originally extended much further to the east, and the new work, the new Gothic church begun in the 1220s, although what we're looking at here is really the transept in the very beginning of the nave, begun in the 16th century.
The ancient church didn't provide any support for the massive new cathedral. Leaving the nave unfinished was a fundamental error. The huge weight of the towering walls was pushing them outwards.
They went to all the trouble of digging 10-meter deep foundations, which would have been a huge undertaking, and yet they didn't finish off the nave, which is the essential part to keep the rest of the cathedral standing.
Fixing the damage caused by the collapses finally drained cathedral finances, and construction of the nave was put on hold for a few hundred years.
In the 19th century, a few projects wanted to continue building the nave, but it didn't happen. They couldn't find the money. The next works to be carried out were essentially restoration.
Although construction remained at a standstill, during the Middle Ages, architects realized the walls were on the brink of collapse. A resourceful fix was needed, and fast.
The builders weren't totally blind. They could see the building was struggling. And to stop it from bowing outwards, they installed iron tie bars.
The tie bars literally tied the walls in place, a crude but effective fix that stabilized the cathedral. Fast forward to the 1960s, and modern-day engineers thought they knew better. with almost catastrophic results.
And so it was decided to replace them, but this time not with iron, but with steel tie bars that had less flexibility. And so, whereas the old structure had a certain amount of give and take, it could respond to the winds, the new structure was much more rigid.
By replacing the iron tie bars with steel, a more rigid alternative, the cathedral had lost its flexibility, which left it at the mercy of Mother Nature.
So basically, by trying to modernize the fix, the engineers had actually made the cathedral more vulnerable than it had been for centuries.
With such a fragile piece of architecture, today, engineers keep a watchful eye on any change in the cathedral's stability. Saint-Pierre is closely monitored, using modern technology. Constant Chacoz and his team use highly sensitive sensors to detect the slightest movement.
On this pillar, we can see optical strands fixed onto the structure. Optical strands are very accurate sensors dedicated to the measurement of strain and displacement of the structures. The resolution of these sensors is about 1 micron. Micron is 10 smaller than hair.
1 micron might seem like a tiny amount, but when you've got thousands of tons of stone shifting around, I'd want to know exactly what was going on.
While monitoring for modern-day movement, Guillaume Caron is laser mapping the cathedral in 3D to check for hidden defects in the original construction.
This image is a kind of blueprint, but made from a 3D digital model of the Cathedral of Beauvais. And what is interesting from this information is it's not a manual drawing, it's got from measures. So from this blueprint, or digital blueprint, we can highlight some deformations and to measure exactly, for instance, the distance between each pillars in the cathedral.
Laser scanners bounced high-energy light off every surface in the cathedral, creating a highly detailed picture of the building. It was so detailed, they could see things that weren't visible to the naked eye.
What Guillaume's team has discovered is more than a little disturbing. Beauvais Cathedral in France has a history of engineering issues that date back centuries. Today, modern technology is vital to understanding how best to preserve this fragile building. Guillaume Caron explains.
Using this image, for instance, we are able to highlight that the pillars that are on the southern part of the choir are very nicely aligned, but there are some misalignments between the ones in the northern part.
These misalignments have remained undetected throughout the ages, but reveal a whole new instability threat.
We were surprised by these deformations and the fact that the building is still not collapsed.
To further stabilize the walls, engineers have taken the radical step of installing giant braces.
The braces, they're not pretty, but at least the cathedral is still standing.
This building is clearly a survivor.
Our next story begins in Illinois, where a radical piece of engineering dating from 1900 has inadvertently opened the Great Lakes to invasion.
5 to 10,000 of them just erupting out of the water. I've been struck in the head, one who nailed me right in the thigh.
This Army engineering solution is truly shocking. Chicago, Illinois. In the 19th century, the Windy City grew from a staging post to one of the most influential places on Earth.
Home to hot jazz and deep dish pizza, Chicago is the place to be. And in the summer, there's no place you'd rather be than on the nearby shores of Lake Michigan.
Lake Michigan is one of North America's 5 Great Lakes, the largest group of freshwater lakes on the planet. Jennifer Caddick represents the Great Lakes Alliance.
The Great Lakes region supports a multi-billion-dollar tourism industry, but there's also a thriving hunting and fishing economy in the Great Lakes region as well. People come from all over the world and all over the states to hunt, fish, and recreate here.
By the late 1800s, Chicago's rapid growth posed a problem: more and more sewage.
Back in 1900, Chicago had problems that their sewage, all of their waste were flowing into the Chicago River, and then that was flowing out into Lake Michigan and right towards their drinking water intakes.
To stop sewage from contaminating the fresh water of Lake Michigan, engineers came up with an epic idea: to send the city's waste in another direction by reversing the flow of the Chicago River. Work began on the Chicago Sanitary and Ship Canal, connecting the Chicago River with the Des Plaines River, 28 miles away. The new waterway connected Chicago with the Mississippi Delta and ultimately the Gulf of Mexico, not only solving the sewage problem, but also creating a trade route. However, the ingenious engineers had unknowingly opened up the Great Lakes to a major threat.
I'm stating the obvious here, but connecting 2 waterways that have never been joined before sounds like a recipe for disaster.
This disaster came in the form of an invasive interloper, the Asian carp.
Initially, in the 1970s, the Asian carp were brought in intentionally to eat algae in sewer treatment plants. However, they have since escaped via flooding into the surrounding waterways and are now running rampant throughout the Mississippi Delta and right up toward the Great Lakes.
Asian carp are a highly invasive species that spawn rapidly. They overwhelm native fish, consuming their food and threatening their very existence. By the 1990s, the carp had spread to the Mississippi Delta. Today, they are within mere miles of Lake Michigan, and they are still on the move. Asian carp are not only a threat to native fish, but they can also be potentially lethal to humans. They weigh up to 99 pounds, and when startled, they can leap out of the water unexpectedly. With a tourism and leisure industry worth billions of dollars a year, the last thing the Great Lakes need is Asian carp. To stop the subaqua menace in its tracks, an engineering solution is in place at Romeoville, 30 miles southwest of Chicago. It's an underwater electric fish barrier. Operated by the U.S. Army Corps of Engineers. Colonel Reisinger is in charge.
We are standing on top of Barrier 2 Alpha.
Each barrier unit generates an electrical field reaching across the canal.
As the fish moves from downstream to upstream, they run perpendicular to that electric field generated. When that fish hits that low array field, our intent is to create enough voltage potential there that the fish decides it's uncomfortable enough that it just turns around and goes back down river.
Romeoville actually has 3 separate electric barriers at intervals along the canal, in the hope that if a carp gets through one, it will be stopped by the next.
Further up canal, we have Barrier 2 Bravo, and then even further up from there, we have what we call the demonstration barrier. If that fish pushes through the wide array field and gets into the narrow array field where we have a higher voltage drop potential, a 2.3 volts at the surface of the water,
The electric fish barriers appeared to be a solid solution. However, recent studies suggest that this piece of engineering isn't watertight.
Tests have shown that 62% of fish could get through. The jury's out on this system. It's costing millions of dollars a year, and it might not even work.
If the electric field is undisturbed, it's hard for any fish to get through. However, when a big metal boat goes through that field, it breaks up the field, and fish can slide in the bow wake. Also, if fish are in big groups, the outer fish disturb the electric field and the inner ones can slip through.
With invasive fish potentially slipping through the barrier, regular patrols downstream monitor and head off the problem. Expert fish hunter Justin Peterson has his sights set on carp.
Today we're looking for small Asian carp. This past summer, we caught a silver carp in a marina that was 5 miles from Lake Michigan. Carp are extremely dangerous. They'll jump into the boat. I've been struck in the head. I had a big bruise on my thigh once from one who nailed me right in the thigh.
Justin's methods are just as shocking as the barriers.
Fish get stunned by the electricity. We net them, put them in this tub. Every Asian carp that we catch is weighed and measured. It's a war on carp. I mean, we're at the front lines here, trying to beat them back, and they're trying to keep going forward. At one point, we hit the electricity, and we saw them in the range of 5,000 to 10,000 of them just erupting out of the water.
When you're at war, it's important to know your fishy friend from your fishy foe.
This guy here, that's a gizzard shad quillback, smallmouth buffalo. And this guy here is a silver carp. All these fish, they're stunned. Within 5 minutes or so, they'll be back to normal, and we'll release them back into the water. Minus the Asian carp, we don't release those ones.
Back in Romeoville, U.S. Army engineers are constructing a fourth barrier in an attempt to strengthen their defenses.
Fourth barrier? That tells you all you need to know about the effectiveness of the other three.
Some people would say that building the fourth barrier is a waste of money because you're just pushing the problem along.
With the U.S. Army Corps of Engineers desperately trying to stop the advancing fish, experts are looking into other possible solutions. But to truly protect America's Great Lakes, they may have to turn back time. Romeoville, Illinois. The U.S. Army are locked in a conflict with the advancing Asian carp. However, their underwater electric barrier is flawed. Perhaps there is only one real engineering solution that will work.
Long-term, re-separating the Great Lakes from the Mississippi River Basin is the complete solution. We know that there are many steps between where we are now and that long-term vision. You know, the Great Lakes are my home, and so it's so important to me, and I know to millions of other people, that the lakes are protected not only for our health, for our ability to recreate, but also for our children and grandchildren.
The impact to fisheries and to tourism could be in the millions, if not billions of dollars.
Let's hope they can save the Great Lakes. Stop the Asian carp once and for all.
For our final calamitous tale, we're heading to Germany and a town that's literally cracking up.
It's an earthquake in slow motion.
People thought about a catastrophe.
It's a disaster that's spiraling out of control.
This town is just coming apart at the seams.
This is a nightmare in a land of fairy tales.
The ancient city of Staufen im Breisgau, with its 500-year-old buildings, looks like it's straight out of a fairy tale. But in 2007, an engineering disaster began to tear this town apart. Journalist and local resident Raina Ruther opens up on Staufen's nightmare.
Those who live here around the main square, they heard noise at night. They asked themselves, why can't I close my window? Why does the door doesn't close anymore? Cracks started to appear on one building, two buildings, and people asked themselves what had happened.
The cracks continue to grow and spread.
What you see here is one of the, I would say, main affected buildings in Staufen. It's right on the Marktplatz, right on the market square. It's an earthquake in slow motion. This is what they say here.
The ancient Baroque town hall was worst affected, sinking by 1/3 of an inch.
1/3 of an inch might not sound much, but if your building hasn't moved for 500 years, that's a huge amount.
After just 2 weeks, a staggering 68 buildings were showing signs of damage. And for pharmacist Peter Gasper, there was no cure in sight for this perplexing problem.
We detected some cracks in the walls, and nobody was certain what was the reason or the cause of these cracks. Some people got emotional, some people thought about a catastrophe, and so everybody was worried. If you walk through the house, you can find cracks all over the house.
Anxious residents called in geologists who discovered something extraordinary. Staufen had indeed been sinking, but bizarrely, the ground under the town had now begun to rise. The team quickly zeroed in on the culprit, a project to heat Staufen's town hall with a green energy source.
The Earth's core is extremely hot and full of geothermal energy. To harness this geothermal energy, you need to drill down straight into the Earth's crust.
This heat energy is then drawn up the borehole to the surface, where it powers heating and cooling systems. Drilling began in 2007, just before the town started to crack.
When I heard about the idea, when they wanted to repair the building, that they want to use geothermal energy to heat and cool the house, I said, what a good idea. And the town council unanimously said, what a good idea.
Free energy might sound like good news, but to reach the heat, engineers unintentionally triggered a slow-motion earthquake.
To tap into this geothermal heat, they drilled a hole about that wide, 6 inches, about 140 meters or 459 feet down into the rock from the surface.
There, they reached the water table.
Anywhere on the Earth, if you drill down deep enough, you're going to hit something known as the water table. And this is when water from the surface trickles down and settles at a certain level. That level will differ in height depending on where you are, but it's always going to be there. When they drilled down into the water table, there was an initial drop in pressure, and on the surface, things began to sink.
Loss of water explains the ground sinking, but with the town rising, something else had to be going on. In 2007, the German town of Staufen im Breisgau started to sink, causing damage to many historical buildings. When the geologists investigated, they discovered that the town was now rising. Their first mission was to work out what was going on under Staufen.
After further investigation, the geologists realized the problem. The town was built on this, anhydrite.
Anhydrite was formed millions of years ago by the evaporation of salt water on ancient seabeds. Environmental scientist Konstantin Krinja explains.
So there's basically just a big layer of anhydrates right underneath of Staufen.
This commonly occurring mineral rapidly absorbs water.
So when anhydrate and water mix, it expands and forms gypsum.
The expanding gypsum creates subterranean pressure.
Imagine the layer to be like something like a sponge, and you pour some water on it so it expands or it bulges up right at the spot where you pour the water on it. And the surface itself bulges the same way. So if you have a house standing on top of it, the floor is basically tearing apart.
The geothermal boreholes had brought the anhydrite in direct contact with the water table.
What I have here is a normal diaper. What this diaper has, and basically every diaper has, is that it has superabsorber in it. And this superabsorber is going to act as our anhydrate. And once I pour water over it, it's slowly going to absorb the water. It also increases in volume by quite a bit, and that's the same thing that the ground is doing as well. So this is exactly what's happening underneath of Staufen.
More than 10 years on, and the city continues to rise and crack.
You've got to understand that this is relentless. Slowly but surely, the ground under Staufen is rising.
Parts of Staufen have risen by up to 2 feet, and over 270 buildings are now damaged.
So we're now right inside the town hall, and you see the cracks and the uplift, which has done all the damage to this ancient building. Well, this crack, you see, it's one that starts right down in the basement of the building, comes up here, and you see the damage that has been done here to the building. This is a kind of logbook of the cracks, and when people started realizing, you see that they marked the number of centimeters that the building has moved. So we come up here in February, 6.9, in not even 1 month, in 10 days. Then if you add this all together, it comes at this 15 or 16, even 17 centimeters.
With their buildings crumbling around them, the people of Staufen desperately look for a solution to their anhydrite nightmare. With the city in pieces, local authorities are working on a fix. The first stage was to plug the boreholes to prevent water from the surface from adding to the problem. Local geologist Sandra Heisler reveals how the town papered over the cracks.
When we discovered that the problem was related to anhydrite, we tried to find a solution. It took 2 years to seal the boreholes again.
But sealing the holes from above was not enough, as the anhydrite is still in contact with the ever-present water table.
The pump was installed to draw groundwater up from 460 feet, so that the water level didn't rise any further.
By continuously pumping up groundwater, the process is slowed.
It has gone down from 10 millimeters a month to 1 to 2 millimeters. It has improved, but it's not over yet.
Pumping out the groundwater is helping slow the destruction, but it's not a proper solution. It's like putting a Band-Aid on. But for now, all they can do is keep pumping.
It's impossible to stop the anhydrite from absorbing water. Instead, residents must hope that it will cease naturally in time.
There is no time frame. We can't say it'll be okay for another year, another 10 years, another 20 years. There's no certainty. Nobody says so anyway.
It's estimated that repairs could cost around $60 million. This is one fairy tale that has truly become a nightmare.
I can only imagine how horrible it must be to be living in this town that's literally cracking up around you.